lecture we will develop an integrated model, where in a single model we try and in an integrated model we try to find both Q and R, where Q is the order quantity and R is the reorder level. In the earlier models that we saw in the previous lectures, we had computed Q based on the economic order quantity equation, and then R was computed based on the lead time demand. Now we will try and build an integrated model to see whether there is any slight change in the value of Q that is computed using an integrated model, or is there a slight difference in the cost computations if we build an integrated model involving Q and R. Now let us go back to the basics of inventory, where we draw the usual time versus inventory graph. Now let us say we start at a certain level, which right now we are not defining it either as Q or as IM, and then we start consuming. Now we are going to assume that the demand D, annual demand is D, the aggregate annual demand is known, but at every instance the demand is probabilistic, it is not deterministic as in the earlier examples. So we start consuming this inventory, and let us say we use a curved line to indicate that the demand is non-deterministic. So the inventory drops like this. Now let us assume that there is a reorder level R which we will determine. This is our reorder level R. So when the inventory reaches this R, we place an order. Now the lead time is the time between placing the order and getting it, and let us assume that we get the quantity. When we get the fresh consignment, the stock is here. So the stock gets updated by a quantity Q, and let us say it comes here. Then once again we start consuming based on this, and again when we reach the reorder level, let us say we place another order. But then let us assume that in this cycle, by the time the order comes, the inventory has come down to this position. Now once again the quantity arrives, there is a back order here, quantity arrives, so the stock is updated by a certain quantity Q. So we can assume that this is the Q and this is roughly the same as this, and once again the cycle continues and so on. So the only change that we have made is because of the probabilistic nature of the demand, there can be some cycles where the ending inventory is positive when the stock arrives, and there can be some cycles where the ending inventory is negative when the stock arrives. This is different from the earlier deterministic models where we consistently assumed that the stock will be 0 or the inventory will be 0 when the stock arrives, or in the case with back ordering, there will be back ordering every time the stock arrives. So we could have cycles like this. Now we have two variables which are Q and R. Q is the quantity, which means this quantity that we are going to order, which we will get after a lead time, and R, which is the reorder level, which is the point at which we place the order. So we will try and get both using an integrated model. So now we write the total cost expression for this. So the total cost is made up of three parts. The annual demand is D, the aggregate annual demand is known. So the number of orders per year will be D by Q into C naught, which is the order cost. This is a familiar term. D by Q C naught represents the annual order cost that we will have. Now there is an inventory component, there is a shortage or back order component. So the inventory component will be given by average inventory into Cc plus average shortage into Cs. Cc is always defined as rupees per unit per year, and therefore average inventory is in units. Now it again depends on how we are going to define Cs. We need to either multiply with the D by Q or not. If Cs is defined as rupees per unit per year, then we do not multiply by D by Q. But if Cs is defined as rupees per unit short or rupees per unit, then we have to do that, because expected value of the shortage, instead of saying average shortage, let's use expected ending inventory or expected average inventory plus expected shortage into Cs. Now in this case we are going to define Cs as rupees per unit short. So Cc will be defined as rupees per unit per year, and Cs will be defined as rupees per unit short. So the E shortage is the expected shortage in a cycle, that into rupees per unit short into D by Q will give us the expected cost per year, because there will be D by Q cycles in a year. Now E of S or E of shortage is the expected shortage in a cycle, D by Q is the number of cycles per year, and Cs is rupees per unit short. So all these when multiplied would give us expected shortage cost per year. Now we have to start defining this as well as this. Now in order to do that, now let us call the expected ending inventory as E of ending inventory. Let us call it as E of ending inventory. Now expected ending inventory or expected beginning inventory will be expected value of ending inventory plus Q, because in any cycle if there is an expected value of the ending inventory, for example if there is something here, then the cycle begins with an addition of Q. So expected average inventory will be beginning inventory plus ending inventory divided by 2, which will be, this is the beginning inventory plus ending inventory divided by 2, which will be expected value of ending inventory plus Q by 2. So now when we substitute, we should now start writing this. Now we call this expected shortage as S bar of X as the expected shortage, and then the expected ending inventory will be, what is the expected ending inventory? Expected ending inventory is the difference between the reorder level and the lead time demand, because when we reach the reorder level we place an order, and when there is a lead time and there is a lead time demand, so we expect that we will meet the lead time demand using this reorder level. So R minus expected value of lead time demand will become the expected ending inventory, because there could be some cycles where there is positive inventory, there could be some cycles where there is negative inventory. That would depend on the actual lead time demand, but we are not modeling the actual lead time demand, we are modeling the expected ending inventory. Therefore expected ending inventory will be R minus expected value of lead time demand. So expected ending inventory will be R minus F of X, where F of X represents the expected value of lead time demand, or we could use slightly a different notation, we would not call f of x here, we would say r minus expected value of lead time demand. So, now substituting in all of them, we would get T c is equal to d by q c naught plus q by 2 plus r minus let's also call it f of x. So, r minus f of x into I c plus s bar of x C s into d by q. Now, partially differentiating this with respect to q and r, we can get the optimum values of q and r, which are the two variables. So, partially differentiating with respect to q, so dou T c by dou q equal to 0 would give us minus d by q square c naught plus I c by 2, because the expected value of the lead time demand does not depend on the order quantity. So, it does not have any effect. So, plus I c by 2 minus s bar of x C s d by q square equal to 0. So, this on simplification would give us q equal to root of 2 d c naught plus s bar of x C s divided by I c. So, this is the equation for the order quantity in the integrated model. So, this is our first equation. Now, differentiating with respect to r would give us, this has no effect, this also has no effect. So, there is a I c which is here from here, I c plus dou of s bar of x by dou r into C s d by q equal to 0. This is what we get, because S bar of x represents the expected shortage. So, this will depend on the reorder level, because shortage happens when lead time demand exceeds the reorder level. So, S bar of x can be defined as integral r to infinity x minus r f x dx. Now, when we differentiate this with respect to r, we would get a minus term here, which comes from the x minus r. So, differentiating and substituting in this, we would finally get the expression integral r to infinity f x dx will be equal to ICQ by DCS. The minus term comes from here, from the partial derivative we get a minus. So, minus goes to the other side, ICQ by DCS would give this. So, this is our second equation, which is this. And our third, of course, is the expression for S bar of x. So, we have three expressions which come here. This derivation is quite similar to the earlier one. If we see very carefully, it is very similar, because we still have that same term ICQ by DCS, which we wrote in the previous lecture as QCC by DCS, which represented 1 minus integral, which is kind of represented the area under the curve. So, in some sense, in the previous expression we got the value of R directly from this. This is a well known equation for economic order quantity, with the only change that S bar of x comes explicitly into this function. Earlier we did not have this portion, so we had Q equal to 2D C naught by IC. When we separated Q and R, we got Q equal to 2D C naught by IC. Now, because we brought R into the picture, we are getting another expression plus S bar of x CS. So, in some sense this derivation is very similar to the earlier one. And then when we want to use it, how do we compute the values of Q and R, which is the purpose of this derivation. So, we explain the computation of Q and R through a numerical example. So, let us go to the numerical example here. So, we try and use the same example for the purpose of comparison. So, we assume D equal to 10,000 per year. So, we are going to assume C naught equal to 300, IC equal to rupees 4, CS is equal to rupees 2.5 per unit back ordered, and we want to find out Q. And we also assume that the lead time demand follows a uniform distribution between 150 to 250 with 200 as the expected value. In the earlier discrete case, we took from 100 to 300 and we followed a discrete distribution. Now, we are going to assume that it follows a uniform distribution between 150 to 250 with 200 as the expected value. We had already seen how the uniform distribution will look like. So, it is like saying this is how the lead time demand will look like. So, this is from 150 to 250 with equal probability with the mean at 200. So, we now want to find out Q and R as well as TC. So, first in order to find Q, we know 2 D C naught plus S bar of x CS by IC. We do not know the term S bar of x. So, if we know the term S bar of x, we can find out Q. Now, let us go back and see what we require to find out S bar of x. To find S bar of x, we need integral r to infinity x minus r f x dx. So, if we know r, we can find S bar of x, because f x is known. So, integral x minus r f x dx. So, in order to find S bar of x, we need r. And now we want to find out how do we find out r. So, in order to find out r, you have again once again r to infinity f x dx is I C q by dcs, which means you need q. So, essentially to find q, you need S bar of x. To find S bar of x, you need r, and in order to find r, you need q. So, what we do is you start with a simple assumption that S bar of x is 0 and then get q. Now, use this q to get r, use this R to get S bar of x, come back and recompute Q and use a kind of an iterative algorithm which will effectively get Q and R to converge into their ultimate optimum values. So, first begin with S bar of x equal to 0. So, iteration 1, S bar of x equal to 0 would mean Q equal to 2 into D into C naught by IC. So, Q is equal to 1224.74. We have computed the value of Q, Q equal to 1224.74. We now use this value of Q in order to get R. So, the corresponding equation is integral R to infinity. So, integral R to 250 in this case, it is a uniform distribution, it does not go up to infinity, it has an upper limit of 250, R to infinity fx dx. So, fx is 1 by 100, so 1 by 100 dx is equal to QCC by DCS. So, 1224.74 into 4 divided by 10,000 into 2.5. So, this 1 by 100 will come out. So, this is 250 minus R is equal to. So, we would get 250 minus R is equal to this quantity multiplied by 100. So, this is 1224. So, this on simplification would give us 0.1959, 1224.74 into gives us 0.1959 or 0.196. Now, this is 0.196. So, 250 minus R will be into 100, which would give us 19.6, from which R is equal to 250 minus 19.6, which would give us 230.4. Now that we have the value of R, we can now use that R here to get S bar of x. So, S bar of x will become integral R to infinity x minus R fx dx. So, integral R is 230.4 to 250 R to infinity x minus 230.4 by 100 dx. So, this would give us x minus 230.4 the whole square divided by 2 into 100. So, this is on the upper limit it is 250, on the lower limit it is 230.4. So, the contribution will be 0 from the lower limit, from the upper limit it will be 19.6 the whole square by 200, which would give us 1.918 as the expected value of this. Now, we have to use this 1.918 into this equation to go back and compute Q again. We show that somewhere here. So, the new computation of Q will be root over 20,000, which is 2D C naught plus S bar of x into CS, which is 1.918 into 2.5 divided by 4, which would give us 1234.5. Now, we can use this 1234.5 into this equation and compute R again, and once again use this R to compute S bar of x and keep iterating till the values of Q, R and S bar of x converge. So, let us assume that Q has converged to 1234.5, let us assume that R has converged to 230 and S bar of x has converged to 1.9. So, finally, we can compute the total cost from this equation, and for these chosen values the total cost TC will be D by Q into C naught, which is 10,000 by 1234.5 into 300 plus Q by 2 1234.5 divided by 2 plus R minus expected value of f of x. Let us say R is 230.4, expected value is 200, so plus 30.4 into Cc 4 plus S bar of x, let us say is 1.918, which is say 1.9 into Cs into D, which is 1.9 into 2.5 into 10,000 divided by 1234.5. So, this on computation would give us this is 2430.13, which is the order cost component. The carrying cost component will be 2590.6 plus shortage cost component will be 38.48, and this would give us a total cost of 5059.2. For the same illustration, when we had deterministic demand, our total cost was about 4,900. Now, when there is the demand is non-deterministic and follows a uniform distribution, we get about 30 extra units as the safety stock or the buffer, and then we have an expected shortage of about 2 units in every cycle. So, this is the effect of having the integrated model. Now, integrated model has given us values which are very close to what we had independently found out. For example, when we use the normal EOQ model, we had 1224.74, here we have 1234.5. We also know that in practice the slight difference of about 10 units is not going to make a big impact. Many times vendors may not be able to give accurate quantities such as 1234.5 etc. It is also uneconomical to do that. So, we would choose a convenient number like 1250, which we used for earlier illustrations. So, there is not much of a change here. Similarly, there was not much of a change here. 230.4 would gives us a service level of about 80% and so on. So, this is also comparable and the total cost is also comparable. So, either one could use the integrated model or one could simply separate the order quantity computation Q and the reorder level computation R separately, and then depending on the distribution of the lead time demand, calculate the reorder level and use it, so that the overall cost is minimized. Now, let us come back to one more aspect of probabilistic inventory models, something that we had already seen and then something that is going to have a large implication in the way we order. In an earlier illustration, we had calculated the safety stock assuming a normal distribution So, let us go back to that example. So, we first said that the annual demand is 10,000, but we also said that the lead time is 1 week, and we also assume that weekly demand follows a normal distribution with mean equal to 200 and sigma equal to 25. Now we worked out a certain computation and said that if lead time is exactly 1 week and if the weekly demand follows a normal distribution like this, if we want a service level of 95%, what is our safety stock? This calculation we did in the earlier lecture. So what we did was we went to the normal distribution and find out the Z value at which the area was 0.95 and the Z value at which the area is 0.95 happened to be for Z equal to 1.645. And then we said Z sigma is the safety stock. So 1.645 into 25 which would give us about 40 units as the safety stock. Give us 41.125 units as the safety stock. Now let us look at the situation, what happens when lead time is equal to 2 weeks. So now when lead time is equal to 2 weeks, of course in this case safety stock is 41.25. So reorder level in the case of 1 week is reorder level is equal to expected value of lead time demand plus safety stock, which is 200 plus 41.25, which is 241.125. So this is the reorder level here. Now when lead time is equal to 2 weeks, expected value of lead time demand is 400 because weekly demand has an average of 200. Now we need to calculate the standard deviation of the demand during the lead time. Now standard deviations are not additive, but variances are additive. So what we do is variance of the lead time for the first week is 25 square, variance of lead time for the second week is 25 square. So total variance is 2 into 25 square. So total variance of lead time demand will be 2 into 25 square, from which standard deviation of lead time demand will be root 2 into 25. So if the weekly demand is D and the lead time is L weeks, then the standard deviation of the lead time demand is root over L into D. So this on computation would give us 25 into root 2, which is 35.36. So standard deviation of lead time demand is 35.36. And now once again for a 95% service level, we would have Z is equal to 1.645. So for a service level of 95%, we would have Z is equal to 1.645, which means safety stock is 1.645 into 35.36. This would give us 58.16 and reorder level is equal to 458.16. Now let us try and understand what is the effect or what has happened when the lead time moves from 1 week to 2 weeks. Now this is 241.125, this is 458.16. Now the 400 comes as a contribution of the expected value of lead time demand, and the safety stock, which was 41.125 here, has now increased to 58.16 here. So, as lead time increases, we end up carrying more safety stock. So, it is necessary to keep the lead time small, or alternately, if we had not adjusted the safety stock and brought it up to 58, but in the 2-week case, if we had still kept the safety stock at 41.125, if we had done that, then what would have happened? If in the 2-week case, if we had retained it at 41.125, then the corresponding Z will be 41.125 divided by 35.36, which is 1.16, and for Z equal to 1.16, the area from minus infinity to Z in the normal distribution would now become 0.877. So, area equal to 0.877, telling us that our service level will only be 87.7% if we had kept 41.125 and the lead time increased from 1 week to 2 weeks. So, if there is an increase in the lead time, then there has to be an increase in the safety stock to maintain the same service level. If we maintain the same safety stock, then service level will come down. So, that is the first lesson that we learned. In both the cases, it happened that while the demand followed the normal distribution, the lead time was still deterministic. The lead time was deterministic with 1 week, and the lead time was deterministic in this case with 2 weeks. Now, if the lead time also follows a certain distribution, then what happens? Now, let us call this as now demand during a week. So, demand follows, let us call this as mu demand as the mean and sigma demand as the standard deviation of the demand, and now lead time also follows a distribution. So, let us call mu L as the expected value of the lead time distribution and sigma L as the standard deviation of the distribution of lead times. So, in this particular example, both demand as well as lead time are following certain distribution. Now, in such cases, the expected value of the lead time demand, is equal to expected value of demand into expected value of lead time, which is mu d into mu L. The standard deviation of lead time demand is now given by root over mu L sigma d square plus mu d square sigma L square, mu d square sigma L square. Now, let us understand the effect of this when we apply it to the same numerical illustration. Now, we have seen a case here where demand follows a normal distribution with mean 200 per week and standard deviation 25 per week. So, let us say mu demand is 200 per week and standard deviation of demand is 25 per week. When we looked at this case, mu lead time is 2 weeks, but standard deviation of lead time was 0. Now, let us look at a case where mu lead time is 2 weeks and standard deviation of lead time is also 2 weeks. Now what happens to our expected values? Now the expected value of lead time demand is simply the product of mu d and mu l. So it is a product of 202, which is 400, which was exactly the same here. Expected value of lead time demand was 400. Now the only difference that happens is in the computation of the standard deviation of the lead time demand. So this becomes root over mu L, which is 2, into sigma d square, which is 25 square, plus mu d square, which is 200 square, into sigma L square, which is 4. So this becomes root over 625 into 2, 1250, plus 200 square is 40,000, $160,000 plus 160,000. So this will become 160,000 plus 1250 root over 401.6. So standard deviation of this would become 401.6. So standard deviation is given by the formula mu L into sigma d square plus mu d square into sigma L square. So we do have this d square term that keeps coming in. So this is roughly of the order of mu d into sigma L. So our mu d is of the order of 200, sigma L is of the order of 2. So this is of the order of 2 into 200, which is 400. So the standard deviation of lead time demand becomes 401.6 in this case. Now what happens is your safety stock should be Z sigma. Now for a 95% service level, we have calculated Z equal to 1.645. 1.645. So Z sigma, which is the safety stock, is 401.6 into 1.645, which is 660.56 units. So now the same scenario here that we saw when the lead time did not show variation, which means sigma lead time was 0, gave us a safety stock of 58.16. The moment we have the lead time also showing variation with the sigma and sigma equal to 2, we realize that the safety stock has moved up to 660.56 units. So the safety stock itself is about 3 weeks of inventory is held as safety stock, and we already know that such a safety stock is never going to be consumed. So much of worth of inventory is going to remain as safety stock at 95% service level. So the lesson is this. Now if we have to choose between suppliers, the ideal situation is something like this, where the lead time is small, the lead time is deterministic, the lead time does not show any variation. So once the lead time is small, all we do is simply have a very small amount of safety stock. Second is the lead time is slightly larger, but it is still deterministic and does not show any variation. Now in this case the safety moves up a little bit from 41 to 58. The third scenario is when the lead time shows variation, automatically the safety stock shoots up. For example, if we went ahead here and computed the case where lead time is actually 4 weeks. Now let us look at a case when lead time is 4 weeks, but then we are not looking at any variation. So lead time is 4 weeks. Now sigma lead time is 50, root over 4 into 25, which is 50. Safety stock is equal to 1.645 into 50, which is roughly 164 is 82. It is roughly 82. So if we had a situation where lead time is 4 weeks but does not show variation, safety stock is 82. But if the lead time is 2 weeks but shows a variation of another 2, the safety stock is 401, safety stock is 660.56. So it is always advisable to go for a supplier who has less variation in lead time, and lead time may be higher, but then the supplier is very sure about delivering it in a certain amount of time. So the most critical thing is to understand the variation in lead time and the effect of such a variation on the safety stock. So it is always good to choose, if you have to choose between two suppliers who even has a higher lead time but definitely sticks to it, versus another person who has variation in lead time. So variation in lead time is not desirable. It is always good to go for a supplier who has no variation in lead time but who can stick to the suggested lead time. So the variation in lead time is going to play a major part in our supplying, in our choice of suppliers and in the purchasing policy of the organizations. We will see some more aspects of this effect of lead time, particularly in the context of supply chain, and we will do that in the next lecture.